Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to the Into the Impossible podcast, a production of the Arthur C. Clarke Center for Human Imagination at UC San Diego. I am your very fearful host, Brian Keating, co-director of the Arthur C. Clarke Center, and today it's a great privilege and joy to welcome a friend from a completely different discipline in cosmology, and that's none other than Dr. Martin. I just had a PhD student graduate. His name is Martin, so my 16th student got slipped in there, confused with you. Dr. Adam Riess. Adam, sorry for that slip-up. How are you doing today?
I'm good. How are you?
I'm doing good. We first met. I was trying to think back when we met, and I realized it was a while ago, and that was probably during this Templeton Foundation sponsored Young Scientist competition. Blah 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 to find the best scientist under age 40, which, I have to say I did win. And what I'm curious about, I think all my listeners are curious about, are you ever going to get over that, Adam? Are you ever going to be able to live that?
I'll tell you, I've had kind of an inferiority complex since then, especially around you.
Sure.
It was what I remember. Right, it was Charlie Towns' 90th birthday.
Yeah.
And he was at Berkeley.
Yep.
And and it was an interesting time, lots of intellectual discussion. And I remember you were presenting results, I think early bicep results.
Yeah, it was designed with bicep. We were about to commission it at the South Pole. And that was right a couple months before we actually ended up shipping it out of town and bringing it down there. And, I have to say they did a pretty good job, the organizers, because I think the subtext of the symposium was to identify Nobel caliber discoveries, and at least between the two of us, we have one Nobel Prize, right. And so I think they did a good job with that. And I was thinking about you, and I was preparing for the show, and there's a quote, and I have it in my book, and you're a major character in the book, as you know, but in the book I say a quote from T.S. Eliot, who's a Nobel Prize winner in literature. He said, "The Nobel is a ticket to one's funeral. No one has ever done anything after he got it." Now, I have to say, I think you're a counterexample to this laureate, Eliot.
Hopefully rumors of my demise have been greatly exaggerated.
But the other thing I remember about you is every conference where we've ever been at together, I always note that you listen with one ear, but you're always typing, you're always working, you're always thinking, pondering. And I wonder, first question I have, because I want to get into some of the weeds, technical weeds, but I think I asked my listeners for some questions for you, and a lot of them want to know what's it like personally, what kind of routines, what kind of habits, and so first of all, can you just tell a little bit about where you grew up, where you're from, and talk us through a day in the life of Adam Riess.
Sure. So I grew up in New Jersey, kind of central New Jersey, pretty normal, I guess I would say typical period. Played a lot of soccer in school, hung out with friends, was always interested in science, though, without a doubt. And certainly the big, I would say, catalyst for me really was a summer program that they ran in New Jersey called the Governor's School of Science. And so they pick 100 students throughout the state to come for a month during the summer between, I think, junior and senior year. And that during that time, you would take sort of advanced courses and get exposed to certain kinds of material. And at that time, I took a course in relativity, my first sort of exposure to really weigh out science. And, I found special relativity to be just mind-blowing. I mean, I thought it was just, anybody who ever takes a little relativity knows, or anybody who's watched Star Trek knows these concepts of, aging, changing as you travel through space at great speeds and lengths contracting. And that whole thing seems like science fiction, and yet that's the real science. So that got me pretty fired up to pursue physics. And then I went to MIT, got my PhD at Harvard, and worked my way from Berkeley as a postdoc to the Space Telescope Science Institute and Johns Hopkins. And a typical day for me, I sort of wear two hats. I work on calibrating the Hubble Space Telescope, which I really enjoy and is important for the kind of work I do. And then I teach at Johns Hopkins. I teach the sort of big intro to astro, sort of Astro 101-ish sort of course. I have a number of postdocs and graduate students, and mostly we're just engaged in research, trying to understand the nature of the universe.
And a question that people wanted me to ask is, what would you do if you weren't an astronomer in the parallel universe?
Wow. That's tough. I really like history quite a lot. So I was a minor in history. I'd certainly thought about something in that world. I also have a number of friends who made the jump from doing data analysis about the universe to data analysis of various kinds of financial or market data. I don't know. I mean, there's so many interesting things out there. It's hard to say.
Mm-hmm. And another kind of, this is the Barbara Walters section. So, if you break down in tears, I'll edit that out. Outside of work, you mentioned soccer. Do you still play that? What kind of hobbies do you have outside?
So I like sports. I love music. And so I spend a lot of time listening to music, movies, books. Also, I have a young family, 2 kids, 3rd grade and 10th grade. And so, there's, as we all know, especially during this time, there's a lot of homeschooling going on. So I'm, interested in quite a lot of things.
And in terms of how you got to where you're at, career-wise, et cetera, what would you attribute it more to? Is it something that you had innately, or was something that was kind of brought out in you, maybe by an educator or a mentor? Well, first of all, did you have mentors? I know Bob Kirshner, et cetera, was your PhD advisor, right? And we are friends as well. And he's renowned for his mentorship. But have you had mentors in other fields?
I've been very fortunate. I've had wonderful mentors, and I've also been lucky to be at some great institutions and to work with fantastic facilities and even great colleagues, even people who weren't formally my mentor. But I was on one very large team in the beginning, the High Z Supernova team, and there were some really great mentors. Just to sort of, you learn the way science is done was so important. But, I would say for me, curiosity, a very strong curiosity has been a driving force. I don't consider myself the smartest person in the field, but I feel like I make up for it in being fairly dogged in my pursuit of puzzles.
Yeah. As I said, literally, I don't know of anyone who has a harder, working reputation than you. And in terms of actually just witnessing you, they say a man's character, a woman's character is revealed when they think nobody's looking. I remember once, I was driving down the street near a synagogue that I was going to, and I saw the rabbi pull out, and I was wondering, is he going to cross the double yellow line? Nobody's watching. He had to go the opposite, and he didn't. He waited for and I was like, that's a true sign. So I think it's certainly true that you have that. I wonder, when you get to the high, and this will be kind of the last question. Well, there's one more question from my wife that she wants me to ask you. But do you ever get this, in academia, we have this kind of Hunger Games that I call the academic Hunger Games, where you start off, you're at MIT, one of the most competitive places in the world. Then you have to beat out, get good grades there, get letters of recommendation, go to graduate school, get a good, thesis project, work really hard, write some papers, get first author, do this, get a postdoc, get a faculty job, and then eventually the Nobel Prize or get promoted. Do you ever feel like that scheme is maybe broken or detrimental mental health wise? And I'll have one follow up to that. But how do you feel?
I think that is not a great scheme, as you describe. I feel lucky in that I did not feel compelled by that scheme. Early on, I had decided science was really interesting to me, and I would pursue it as long as it was fun and engaging, but that I wouldn't pursue it for checking certain boxes along some path. It was not part of my success plan that I had to even become a professor. I sort of wanted to get a PhD and spend some time in the field. And so I think that if people find themselves trying to, check boxes, complete a list to get to a certain place, they're probably in the wrong field, because science is a lot of fun if you're driven by your own sort of curiosity and passion. I would say, like most things, most occupations. And so, if you feel that way, you might work really hard. From the outside, people will think you're working hard. But, from the inside, you might feel like you never work a day in your life, because, if what you're doing is so compelling and interesting. And, as I said, we're blessed that science is one of those kinds of fields that draws people who are just sort of curious and passionate. We don't have to, undertake some of the things that we do in science. We do them because we want to know the answers, and other people do too.
Do you ever feel this kind of contrasting set of emotions that some academics have told me about, and even I felt myself? Kind of there's a contrast between fear of missing out, fear of not being cited, not being credited, attributed, and then there's kind of the imposter syndrome, which is almost the opposite. Do you ever, what are your feelings about those two conflicting emotions?
Yeah, those are great questions. I think early on, in terms of the imposter syndrome, right, I sort of realized for most of us in science, there's a, very narrow niche that we really become quite knowledgeable about. And so, I was able to sort of recognize, it's really just that niche that I know. It's not, the broader picture. And then, when, the Nobel Prize happened, first of all, as I said, it was never really my goal or target. And second of all, I quickly realized, it's not an IQ test. It's not a ranking of great physicists. It's for people who, for the most part, were lucky that they were in a right place at a right time and contributed to a discovery. And that really could be, almost anybody in the field. And so I feel like I'm not Einstein, and I would never pretend to be. And I'm sort of satisfied saying, I have expertise in a tiny niche, and I was lucky. And that's, I don't have to impersonate anybody. That's the truth. So.
Yeah, well, it's rumored that Einstein made a couple of blunders that I want to get into.
Yes, we did correct some of those.
That's right. So, yeah, very few people can say that they actually, superseded Einstein. I want to get into that. But first, I want to take a step back. When did the astronomy bug, so to speak, first bite you? And where do you view sort of your place in this history of astronomy, starting with the first optical observational astronomer, Galileo, and then you and Brian Schmidt and Saul Perlmutter won really the first Nobel Prize for an optical observational astronomy discovery, if I'm not mistaken.
Right.
How do you view that? Is there a weightiness to that, or is it just, well, like you said, you're kind of doing it for fun? You might be a pro soccer player if this wasn't.
Right. I would not have been, for sure. But yeah. So in terms of astronomy and my first interest in it, I was like a lot of kids, standing outside looking up at the stars and really being unable to fathom what was really out there. But, it was a casual conversation I had with my dad when, maybe I was 7 or 8, with him pointing out that stars are so far away that what we're seeing is really the way they were millions of years ago. And some of those stars may even be gone now. And that, just wrapping my head around that, this kind of image of a star not being there, but the light traveling, it just gets into those juicy issues about, physics and these really fascinating aspects of it. And then in terms of pursuing optical astronomy, again, that's to me where some of the most interesting questions just happened to be at the time that I was going to graduate school. These questions like, how old is the universe? I mean, who would have think in graduate school you could even begin to tackle a question like that? Or, what is the ultimate fate of the universe? And then a number of things happened sort of right at the right time. The development of certain tools for measuring the universe, like these exploding stars called Type 1a supernovae. So my thesis involved improving the measurements and their ability to calibrate the universe. And then that quickly led to these projects that our team and Saul Perlmutter's team did, which was to push those measurements further back in time and look at how the trajectory of the universe, the expansion expansion rate, what we thought would be slowing down. And instead, we found to our great surprise, it was speeding up.
Right, and in that context, I want to take our listeners and viewers back in time. So behind me, if you're watching on YouTube, you'll see an image of Galileo Galilei's prison, where he was imprisoned in 1634 or so after writing the Dialogo. And there's a wonderful new book we had on Mario Livio recently to discuss Galileo in this book. But I noted when I was talking to Mario that Galileo didn't. It's a pretty beautiful prison. I think Bernie Madoff would trade
dollar.
And what is it about astronomy, or kind of the cosmological, that, without offense to our friends who study, convective flows and condensed matter physics, really excites the mind and really does things that piss off people like Einstein, when he's reputed to have said, when he first saw, Lemaitre's conjecture that there could have been a Big Bang, he said, "Your physics is atrocious." And what is it about astronomy in particular, maybe the connection to cosmology specifically, that irritates and is so provocative in your opinion?
Yeah, I think that cosmology has the kind of audacity to address these really big questions, like, how did this all start and where's it all going? And first of all, there are a lot of people who feel that, well, that's not a question for science. That's a question for philosophy or for religion. And, there's a certain realm in which cosmologists address these things. We don't say why there should be a universe or, what one should do in the universe, but, the sort of the kinematics, the motions, the distances, these are things that we can address, and questions of, well, how long has this been going on? And so, people like Fred Hoyle getting, very upset at the idea of a Big Bang moment, right. Having a strong philosophical view about that. And so cosmology draws us to the possibility of addressing those really big questions, which, is where a lot of controversy can be as well.
Yeah. So moving into controversies, the kind of immediate aftermath of Einstein's theory of general relativity in the early 1920s was something which I think would be nice to revive as a tradition. There's something called the Great Debates, and they took place not far from you in Washington, D.C., and this was famous, these Curtis Slifer debates. And you've actually written a wonderful treatment, I think, in Physics Today magazine, and you've done some writing and expository work for the public. So in that context, it was really professionals debating, the kind of the size and the structure and maybe the kinematics or evolution of the universe. Nowadays, we, so proof, if anybody needed it, that you aren't just resting on your laureate laurels, is that, you're deeply involved in pointing out that there may be a need for perhaps a second series of great debates. So I want to move now to this article that you and I were both quoted in the Symmetry magazine. I think it was about a year ago, called "The 9% Difference." And this is really a startling discovery, which I think you, in all honesty, you played perhaps the first and foundational role in bringing it at least to attention of cosmologists. And then you went through and have been doing some of the most yeoman workman-like work towards understanding what's happening. So very briefly, I know you've spoken about this ad nauseum, and I'll have a link to folks in to the article in the show notes. Can you explain what is this 9% difference?
Sure.
Why does it matter? And
yeah, so over the last 20 years, we have sort of arrived at what we call a standard model of cosmology. This is sort of our greatest hopes and dreams, is to say we understand the universe. And when we say that, we really mean we have a model, a story, there's physics, there's components. We can explain from the beginning to the end how the universe would expand. And I would say that's been very successful. And so ours today is called Lambda CDM, as you know, stands for dark energy, cold dark matter, and the other physics that we know. But the truth is, we don't really understand very well the nature of dark matter and dark energy. So it's very important to keep testing this model. And as you know, and maybe some of your listeners know, some of the most precise measurements we get of the universe, ironically, occurred just after the Big Bang. In the cosmic microwave background radiation, you get a very precise picture of the universe and very precise measurements of how fast it's expanding. And, it's a little bit like if you had a child, they're born, maybe they're 2 years old, you can measure their height extremely well. Now, if we understand this model of the universe, then we ought to be able to explain then how that process continues, how the universe expands over the next 13 billion years. And we should be able to predict how fast it should be expanding today. Just like with that child, you could predict how tall they will become eventually. And then you go out and say, okay, let me actually go measure how fast the universe is expanding today. And what we're finding, I would say with pretty high consistency through multiple techniques and methods, is whenever we measure how fast the universe is expanding today with different methods, we always get a higher number, and quite significantly so, than this very precise measurement at early times, coupled with the prediction based on our understanding of the universe. So it's like you predicted the height of that kid, and then he or she grew to be, 2 feet taller than you expected. Now, that would be really weird with a person, because we've seen many people grow. We know what the growth chart looks like, but we only have one universe. We don't get to say, well, this is what's normal for a universe. And of course, on top of that are these unknown parts, 95% of the universe in the form of dark matter and dark energy. And we don't really understand the physics of them. Cosmologists are very good at giving names for ignorance and making it sound like we sort of know what's going on. We say the simplest version, the most vanilla version of dark matter and dark energy would have these properties. And what we're seeing at some level is the universe isn't quite matching that vanilla description. So, is this going to tell us about a new wrinkle in the universe? I don't know. It's a very hard problem, as you know, to even understand, what exactly that could be. And so many of us continue to work on improving the precision of the measurements and sort of this, the way science works between theorists coming up with ideas of what might explain it, and experimentalists and observers like myself trying to get finer and finer measurements to sort of parse those different possibilities.
And what do you say that, there are a lot of tensions in cosmology, and I think, as I said in that article, the field as a whole could use some good psychoanalysis, perhaps. But there are some who say that not only is the tension overwrought, perhaps there is no tension. I'm speaking of, in particular, a group in Oxford led by Subir Sarkar, and others that say, things like, is there really a Hubble tension? So,
right. And Sarkar actually goes even further and says, is there really dark energy at all?
Right. So what do you mean? What is he, the lead of theoretical physics at Oxford? He's a very esteemed, professor in this field, a researcher. What do you make of these kinds of attacks from eminent scientists?
So, the fundamental problem with dark energy, or the cosmological constant, is the naive explanation is 120 orders of magnitude off from our sort of naive explanation of what it should be or how big it should be. And so in a way that gives infinite rope to people who are going to express doubts, particularly about the data, and say, look, I'm going to not use this data, and I won't use this data. I'm going to throw away this data. I'm just going to cherry pick this piece of the data, and I'm going to do this kind of funky analysis that one normally doesn't do, but I can do in this situation. And as I said, they sort of have infinite rope because it seems so preposterous that there would be, this 120 order of magnitude match, and yet that's what the data actually says. I'm a big believer in not censoring the data in that way. And so when Subir looks at the data, he discards this cosmic microwave background data and baryon acoustic oscillation data and lensing data and knowledge of the mass we have of the universe, and ultimately ends up with the closest he can get to get away from dark energy is to actually have an empty universe where there's zero matter or dark energy. And that's still in tension with the data. And so, I think we learn the most by sort of letting the data sort of guide us through the universe, because our ideas have not been very successful, sort of ab initio. Einstein himself, was sort of fooled early on in his career in trying to understand the universe and how it would expand and what the dynamics were.
Yeah, and do you think, as I've kind of spoken out with some other authors and intellectuals on the show, there is this notion that scientists are somehow immune from the very biases that make human beings, such as confirmation bias, being one of the ones that's pretty prominent, going back all the way to Galileo, and even his own imprisonment was somehow related to the fact that at all costs he wanted to kind of bolster the Copernican hypothesis, even when the examples he used were wrong, and he didn't use the best data that he had already collected, as Mario points out in his most recent book. But I think nowadays, we kind of have this, clinging to your priors or reversion to your priors. And it's almost like the priors are becoming, it's almost like confirmation bias is now entering in as a part of Bayesian, methodology because of this priors that one must apply. And I wonder, with people like Einstein, the thing about him, although it's not really clear if he actually said, lambda was his biggest blunder, the cosmological term. I think Mario goes through and maybe debunks that in an earlier book. But nevertheless, he had the magnanimity and the intellectual honesty to say that, yeah, he was wrong about this expansion. What do you make of the kind of the passion that, in particular, the work that one does? I get these letters every day. Professor Keating, I've discovered, Einstein was wrong. If you help me publish this, I'll share the Nobel Prize with you. I imagine you don't need those. You don't reply to too many.
I answered one of those letters, and it all worked out.
Fantastic.
But, Einstein was given bad information. He was told at the time that the universe was static, that it wasn't expanding or contracting. And at the time, astronomers didn't understand the difference between the Milky Way and the universe. And so, Einstein was not really a victim of his own biases so much as a victim of bad data. And, he was trying to make the best of bad data, given this, incorrect information that the universe was static. He sought a way to bring balance, the tendency of a universe with matter in it to start to collapse if it was static, and some way to oppose that. And he made this remarkable discovery that the gravity of empty space itself can be repulsive, can hold that back. In a way, right, he discovered the greater possibilities, another feature of his theory of general relativity, which then, as you know, sort of went into hiding or dormant for a while as we knew the universe to be expanding, that Einstein wasn't given the right data at the time, and then we sort of re-invoked it. So, I've never really seen it as a blunder of Einstein. I've always sort of seen it as another statement of his sort of brilliance to be able to, in 1916, discover the possibility that empty space can have repulsive gravity, and for us in 1998 to say, I think he was right. So,
well, to provide evidence that it looked like he was right. I always say his biggest blunder was saying it was his biggest blunder. Yeah. Thanks to you.
Exactly.
And your teammates. So showing on the screen here for those watching online that this model of so-called the Big Crunch, and you may know there's another cosmic controversy, as our friends might say across the pond, which is whether or not inflation took place. And this isn't a set of crackpots. I always say the people that email me Einstein was wrong, I always write back, well, let me know what you think about Boltzmann. It's always, they always choose Einstein. Like, you ever play Dungeons?
Somebody else.
Yeah, when you were a kid, I don't know if you ever played Dungeons and Dragons. Sure. But you kill somebody and then you get their hit points, or you hit somebody's army in Risk and you get all their armies. It's like, it doesn't work that way.
Right. You become you get Einstein's mantle if you knock Einstein off his mantle.
And sometimes I see that there's more than one person who's come out and said there's problems with the data, there's problems with the supernova data, there are these issues. I think again, with the higher you fly, as my Italian friend told me in Italian, but I can't remember. The easier you are to shoot down. Because
what people should understand, and I just want to point this out, that cosmology is hard. There's no question. The data is difficult to acquire and analyze. What leads to consensus in our field generally is when, as you know, many different kinds of data that probe the universe in very different ways come to the same conclusion. Likewise, for theory, when many different theorists thinking about things in very different ways come to similar conclusions. And your friends who write you these messages about, I have this theory of the universe, and you wonder, is this right? Is this person a crackpot? We wonder this all the time. I tend to notice many of those people, each of them has a completely different idea. They don't succeed in convincing anybody else of their sort of outlandish ideas. So, this is part of the science process, is we are able to reproduce the truth or reality, whereas, a mistake or an error here or there is generally not reproduced in data set after data set. Likewise with theory, different mathematical ideas are not something that you can develop and come to from a different direction, keep arriving at the same place. And so it's this reproducibility that really defines what is special, I think, about science, and generally leads us to think we're on the right track.
And so, getting back to this, discussion of another controversy, the existence or lack thereof of an inflationary epoch. This has come alongside it. I think both the discovery of dark energy and the discovery or cosmic acceleration and the discovery of inflation, or things that are consistent with inflation, bring up very startling conclusions about, in one sense, the very early universe, which has a concomitant kind of co-equal prediction that we live in a multiverse if the inflationary model is correct, because it's almost impossible to develop models of inflation that don't feature multiverse-like extensions to them. You can, but it's very difficult according to the 2 or 3 foremost proponents of it. And so that's led people, as it has with the discovery of the accelerating universe, to speculate about the implications of the theory. I want to get into that a little bit later. But first, on the technical side, do you feel that some of these implications of just acceleration itself, do you feel like they will be found to be related to, say, the inflationary epoch? I mean, they're both exponential, potentially exponential expansions operating over different timescales.
Yeah, I'll even throw a third in there, which is, the Hubble tension right now is the appearance that there's still some sort of anomalous additional expansion. And, we feel like there could be maybe as many as 3 episodes, inflation, acceleration, and whatever's causing the Hubble tension, which could have been, anomalous expansion is sort of at an in-between time, shortly after recombination or before recombination. Mm-hmm. These are things that are not easily addressed in our understanding of gravity without invoking some kind of energy of empty space. And so, it just may be that, this is really an area of physics that we're just beginning to sort of scratch the surface of, that, we see the universe go through occasional periods of this anomalous expansion. We're attributing it to excess energy in space. And, maybe at some point we will understand how they have some relationship between each other, some ability to even predict or connect them. I mean, I'm not aware of it right now, but it's very compelling when you see something happen, for certainly the second, if not the third time, to start saying, haven't I seen this movie before? Sometimes, our colleagues like to talk about anytime you invoke something strange going on, well, you're invoking the tooth fairy, and you're allowed to do that maybe once. And my question becomes, how many invocations of the tooth fairy is it exactly to have inflation and acceleration and maybe even Hubble tension? Is that 1? Is that 3? It's hard to count.
Yeah, and certainly, our colleagues are nothing if not creative in the theoretical sense and coming up with ideas. And I do want to talk to you about one idea that's my pet favorite for a resolution potentially of the Hubble tension, and that's the existence of primordial magnetic fields. And I heard talk where you gave recently on another competing YouTube channel, so I'm not going to mention his name. No, I can't pronounce his name, but
yeah.
Cosmology lecture you get.
Yes.
And you were sort of a little bit dismissive of the idea that, you made a kind of an offhand quip that, when we were in graduate school, we were taught, if you can't explain something, but now you may remember from my talk.
But we did that only because it was so hard that it was sort of like cover for anything. It was like, and in the area we all know we don't understand, there's magnetic fields, right? Yeah. And so there's a certain sensibility to sort of say a phenomenon we don't understand, the excess Hubble expansion, and a thing we don't understand. Maybe they explain each other. I mean, I don't know.
Right. Well,
one of the leading ideas now may be that, if you have primordial magnetic fields, then these can change the way the early universe operates. And this quantity we like to calculate called the sound horizon that lies underneath the ability to predict the Hubble constant or expansion of the universe.
So for my little quip and retort to your quip, as Arthur C. Clarke said, for every expert, there's an equal and opposite expert. So for every quip, there's an equal and opposite quip. So I kind of view primordial magnetic fields as the parents instead of the tooth fairy, because we know that magnetic fields exist in all structures that are gravitationally bound today. We have yet to discover a truly all-pervasive cosmological field that's not gravitationally bound. But I gave a talk at Hopkins last May, I guess it was, and I mentioned that there's a lower limit on a primordial magnetic field strength from the non-observation of these TeV blazars that do not have these GeV halos around it. And so now the lower limit is pretty breathtakingly small. You talk about fine-tuning. It's about a micro nanogauss, as I like to call it. And the limits that we're making from CMB experiments, such as polar bear, Simon's array, ACT, SPT, BICEP, et cetera, are on the level of about a nanogauss, maybe a little bit lower than that. But a lot of the tests that we're looking for that probe a magnetic field strength are relying on the CMB's, what are called the CMB's power spectrum. So you make correlation functions, you Fourier transform them, and you get the power spectrum. That sort of sensitive to the magnetic field to the fourth power, I believe. So it's very hard to make progress against things that scale as a fourth power. It's sort of the first measurement you do, you pick all the low-hanging fruit. But there's another complementary approach that we're starting to invoke with our colleagues and the Simons Observatory and other projects around the world, which is to look for Faraday rotation, which is linear in the magnetic field strength. So that will produce a signal that would cause polarization rotation. And for those reasons, I think
you need a background source for that.
Well, you use the CMB's E modes. So we know the CMB has E modes, and then we know the plasma had free electrons. And so the question is, do those fields survive to? And it's exactly the epoch that you care about. You always have this really prescient, observation that how do you define the early universe? Well, it's when neutrinos are important.
Exactly.
And I think you could say, if you could find these magnetic fields, which are ubiquitous, I mean, we have them in our bodies and we have them in our solar system and beyond. So, if you could find that, I think that would require the least modification to the laws of physics. I always feel like, Nima Akani Hamed always says, like, people that look for violations of the standard model, people like me, looking for these departures from the so-called standard model, are really, maybe going down a fool's errand, because it's very hard to break the standard model.
It is, But that's even when we talk about things like the Hubble tension, we're looking for a wrinkle, not, a paradigm change. And so, like you said, something like a magnetic field in the early universe, I think probably magnetic fields is sort of in the same position that the cosmological constant was 20, 30 years ago, where people would say, well, I don't know really how to calculate or figure out what it should be a priori. I guess it's zero. And, zero wasn't a good guess, and it was not really, we didn't have a profound reason why that ought to be. But, physicists like simplicity. So if something isn't rearing its ugly head at the moment, right, then we say, well, it's zero. So maybe magnetic fields primordial have been, zero for so long. And then at some point we'll go, actually,
There's this meme that I know that part of your productivity stems from the fact that you don't use social media.
Yes.
Unlike me. Yes. So there's a meme on Twitter.
That's my secret weapon.
There's a meme on social media that when everybody says something about like new cure for COVID or whatever, cancer, and that you should always add, just say in rats, or, just say mice. It's always in mice, and it's always like 8,000 cups of coffee equivalent in a mouse will kill you. So I always say, the equivalent in cosmology should be just say dust. And one of the things I did the research in for my book, and I came upon some papers that you wrote with Bob Kirshner and others back in the 90s and mid 90s. Again, very trenchantly observing that there could be prosaic explanations for what we were seeing. And I wonder, and even things that come about now, like this Tabby star or you see things, these Oumuamua or things like you see all this evidence for literally the litter of the cosmos, basically dust. I interviewed Ann Druyan, who's Carl Sagan's widow, on last Friday as well, and we were just talking about the pale blue dot is really this speck of dust floating on a sunbeam, and it's really just highlights the pervasive kind of ability for dust to stymie observations on one hand, and on the other hand to kind of point directions to new fields of research. So I wonder, you've done some research in a really wonderful paper I'll put a link to as well, which is just like this you're just doing the work. I mean, you're saying like Cepheid crowding. I don't want you to get into it now, but you're actually looking at the systematic errors. So the difference between a statistical error, which can be reduced with more data, and a systematic error that's intrinsic to your system or the cosmos itself is very profound. And it's much harder, I think, to get rid of these systematic errors. So are there still systematic errors that you would point to? I mean, I always wonder, like, how well do we know the astronomical unit? What if it's off by 1% or 0.5%?
Pretty good with that. We've done radar ranging off the sun. The way you find systematic errors is you give talks and you listen to your colleagues, and your colleagues generally ask good questions. And instead of just dismissing them, there can't be that, right? You kind of, after the talk, okay, make a little note of that, and you sit around, you try to think of ways to answer your colleagues. And, it might seem at the time, especially, when you're first starting out in research, those are such unfair questions, how can
or when you're about to publish a paper
that's right.
Startling.
Right. That's right. But, you really will do well to listen to those critics and then try and come up with an experiment or a measurement or a test. And if it succeeds, go back to them and say, is this convincing or not? And then, continue the process basically until, we'd like to say, and it's true, Carl Sagan said, extraordinary claims require extraordinary evidence. And so,
I brought that. I actually had his daughter on and as well as Michael Shermer on recently. And I said, I don't like all of a sudden my students comes to me with some data and I say, that's data, but I need extraordinary, like it's either good or it's bad. It's just how tight in the kind of Bayesian prior does
but it's right. And in a way, how large a claim are you making? How much supports this? And so, I've been fortunate to be around a few things that required extraordinary evidence. And it's, it's hard, and it takes, it's more than any one investigator or team or group can do. It takes really the community, firing at things in different ways. And, we've all seen, very well, you wrote a book about a result that, sought the extraordinary evidence and, learned about, the difficulties of dust. And, the community is pretty good at, digging into these things, asking these questions. And, it's rare, I don't know, in my experience, that something that's just flat out wrong survives that onslaught very long.
Yeah, exactly. So I want to turn now, we've discussed that. I think you go through in your talk on this Cosmology channel, I'll put a link to it, what your kind of pet theory is. I mean, to the extent that you're willing to even say there's a pet theory, but I've always wondered, like, how much would you pay for a supernova to go off at like redshift of 5? I mean, wouldn't it just settle everything in your field?
Well, it would be nice. It might even be better if one went off in the Milky Way, because if it went off in the Milky Way, we could measure parallax to it, right? And so we'd skip some of these steps. We use intermediaries to calibrate things, but if one went off, I mean, not too close. I don't want to singe anybody.
Exactly. I was thinking, like, does he want to take out some colleagues?
No. Well, so if I could beam it at certain places, but anyway, no. If we had some in the Milky Way, we'd measure parallax. And we would calibrate these great standard candles, even better probably than we have.
Yeah, exactly. So we talked about different tensions and so forth. Any other tensions that are particularly interesting to you?
There are. I mean, to my view, the Hubble constant tension is probably the largest in significance. But there are other kind of, what we call curiosities. There's something I've always noticed in the cosmic microwave background. You fit the power spectrum as a function of frequency, or L. You tend to get somewhat different parameters over different ranges of L. So when two different experiments basically measure the power spectrum over the same range of L, they tend to get consistent results, which tells me that the experiments actually look pretty good. It makes me wonder if the underlying model is the thing that actually changes with L, because, and you've probably seen this as well. You look at the cosmological parameters around L of 1,000, and maybe you get a Hubble constant closer to 70. Then you do it more like at L of 2,000, and it kind of drifts down to 64-ish. Then you go out to even higher L, 2,000, 3,000, drifts back up into the low 70s. And, as I said, when other experiments remeasure the same patch of sky on the same frequency, they get consistent results. So I'm not as concerned about the experiments as I am wondering. And all these sorts of hints and tensions are more at the 2.5 sigma level. They're not something that all on their own you would draw a lot of attention to. But if you're trying to solve a larger puzzle and you found a solution or a story that weaved in a few of these things, some of the people who work on ways of altering the composition of the early universe have made claims. Not only does it solve the Hubble tension, but it explains some of these variations with L in the parameters. Or not only does it explain the Hubble constant, but it helps with something called the sigma 8 tension, which has to do with the sort of chunkiness of matter in the universe. Some things make it worse, in which case, you go, well, that doesn't sound very promising. But so, you do well to pay attention to sort of all these clues. A lot of people say, well, it's not, 5 sigma. I don't want to hear about it. Well, yeah, but if you're trying to actually figure out the next step, you piece together a bunch of 3 and 4 sigmas, and if you can find a story that ties them all together, then can have the equivalent significance.
Yeah, absolutely. Yeah, I think about that in the context of these topology measurements. I did a podcast with Jan Levin, who wrote a book called How the Universe Got Its Spots, about the topology and structure of the universe. Those are still outstanding questions. Axis of evil, different effects.
Axis of evil, the dark spot, the cold spot.
Yeah.
I mean, there's certainly a few funnies that are hanging around, and I think smart people, go to talks and, write in their notebook and draw a circle around the funnies, and they have their own collection of these are the ones I believe look legitimate. And, they spend time thinking, how can I tell a story that weaves through a number of these?
Yeah, that's wonderful advice. And that segues nicely into a segment I'm going to call the big picture segment, where we take a step back. I mentioned that we met first time 2005 at this John Templeton Foundation search for young scholars. And, of course, the Templeton Foundation is heavily associated with searches for spirituality and the consilience between science and religion. Not that it's to the exclusion of atheists who've won the Templeton Prize, but one question that I've had, for you, the character of your discovery is a little bit different than, say, a blue LED or even a transistor or something like that, or explaining a phenomenon that was known to exist, sort of retrodicting it, as had been done in different cases throughout history. It was really a serendipitous discovery. I mean, you weren't looking for it. I claim in the book, as you might remember, that those are the purest discoveries. But what I'm curious now in relation to Templeton is, does your work have any influence on you, maybe the way that you think about your place in the history of science, or does it affect you personally, religiously, philosophically in any way?
That's a good question. That's a really good question. I would say not very much. I mean, I certainly feel lucky or fortunate to be living in interesting times, as Confucius says. And, I think there's no question that, we will look back on the last 20 years in cosmology as a very special time. We like to call it the era of precision cosmology. But you and I know, right? We went to graduate school, and at the time, people were saying, "Yeah, nobody knows whether there's enough matter to close the universe or not. What the
age of the universe,
nobody knows, what the ultimate fate of the universe is, whether it's going to recollapse or not. Nobody knows, right? The age of the universe and the expansion rate to a factor of 2. And I don't know about you, but I just sort of thought, like, if you show up in a class and they tell you nobody knows these things, probably nobody will ever know those things. I mean, that's just like they're the swords and the stones that are, cast in there, 1,000 years ago, and you're just going to have to live with it. And, you and I got to see a lot of those topple over the last 20 years. I mean, we don't know the answers to everything, but I would say we went from almost like the pre-Magellan view of the world to, post, okay, this is the basic parts on the map. And, I just feel lucky that, we've been around during that time. I would be pretty much just as happy just to have gotten to witness it and just see it and learn about it and get to go back to the last class and go, actually, we know this stuff now.
Now we know this.
Right. Yeah. So, we all, I think, as humans are fortunate to be around during the times when we've learned so many profound things that, address people's basic curiosity about the universe.
Absolutely. So these are questions from lay persons. First one is, do you feel differently in your approach to science now that you have won the Nobel Prize, or do you still feel the same as before?
I don't think I have changed my approach to it very much. It maybe to a small degree it inspires me or reminds me, wow, you never know what's lurking around any corner. Do a basic measurement, do a basic test. You might find something. But no, I think, science is science. Whether you're doing, your physics freshman lab experiment or, something with the Hubble Space Telescope. There's a process. You state a hypothesis, you collect evidence for or against as you find out when you analyze it. That's that procedure. It's a beautiful procedure. It's, science really has, I think, just about the best way of getting to truth on things. We can't answer everything, but, our procedure, if we follow it, is really, really powerful.
That's right. Yeah, absolutely. I agree 100%. Last question about the Nobel Prize, since I cannot resist. I've got you here. I can ask anything I want. You don't have to answer anything. Is there anything about the Nobel Prize that you would change, or is it pretty much okay as it is?
Yeah. I guess the thing I would change is the size of the group that can be recognized. I think it's, this is a holdover from a time when science was literally done by a few people. That, it probably was not very limiting in the year 1900 to say, all right, what are we going to pick? And we don't want it to include more than 3 people. But today, as you and I both know, science is done generally in large groups or teams working together. That kind of division of labor allows us to do bigger and better, more exciting things. We build off of each other's work. We don't just start out and, like an Einstein, say, I was just, having a beautiful thought and I realized something amazing. We really are like, I went to so-and-so's talk and I heard this thing and I thought I'll do one thing a little more. Mm-hmm. So, I wish that the Nobel Prize could go to recognized teams, sort of without limit in size.
Fantastic. Yeah, the Peace Prize does that already, as and you and I know. Okay, final questions, and then I'll take questions from the audience, meaning you. First question I have as there's a concept that Alfred Nobel, of course, was aware of when he endowed his prize, of a will, a material will, where he left his monetary and other possessions, physical possessions, to other people. But there's also a concept called an ethical will, which is also comprised within of Alfred Nobel's will, which is the notion that you have a certain set of values or higher thoughts or wisdom that you want to communicate. And for Alfred, of course, it's the famous catechism of the Nobel Prize themselves, which is for the betterment of mankind. And these discoveries should agitate towards, not just in the Peace Prize, but even in the Physics Prizes, to better mankind. So I want to ask you, in 120 years of life, you leave your ethical will, not your material will, but what do you leave in your ethical will?
Yeah. I think the best sort of guiding advice or light that I think comes directly from science, from physics, from sort of everything I've gotten to experience is to be curious. That curiosity, it's sort of the antithesis, unfortunately, of what I think many people in the world suffer from today, which is a kind of extreme ideology where, that's sort of the opposite of curiosity. Where you go and you say, I know everything already, and I'm just going to beat other people over the head until they know it too. And it never works out that way. Scientists go in with a curiosity, and then you actually open your eyes and actually learn about the way the world actually works. And often you're surprised. In our Nobel work, we were extremely surprised about, what the universe was actually doing. And so I feel like as long as people in the future can hold on to that curiosity to go out, sort of every day question their assumptions and go and look to see, what is real, what is right, what is reality, what is rational, that they'll be well served.
Very nice. So then last of these questions, actually there's a second question. So that's kind of what you would leave in time. Now I want to ask you, hearkening to Sir Arthur C. Clarke's famous movie, 2001 Space Odyssey, there are, of course, these structures. We're not quite sure what they are. They're these monoliths that actually exist and are meant to be encountered by human beings, perhaps. And in fact, some of them drive the plot line forward. I've asked many people this question about if you had to make a billion-year time capsule like such an object, what kind of things would you put on it or in it? It could be material. It could be an equation. I'm going to put up an image that some friend of mine have suggested that they would put up. It's based on the famous wall. This is at Stony Brook University. It's actually made by Eric Weinstein's team.
Yes, I've seen that.
Yeah, and you can actually go to his portal website and click on it, and it takes you through. Now, some people have said that some of these equations would be what they carve into the wall, into their monolith. What would Adam Riess carve into his?
There's this very compelling idea I've seen before about storing all the seeds of all the, every kind of plant vegetation that's ever lived. And you consider the complexity of the process that evolution went through to realize each of those. I might put an example of a seed, a kind of Noah's Ark of the plant world into my monolith. The equations, of course, are very appealing, but if somebody took that answer already, I'm going to go with seeds.
That's cheating, right? Yeah, so the seeds actually, that connects nicely to Andurian's book. She talks about the Russian scientist who first came up with this idea. In fact, during the siege of Leningrad, I believe, when they starved to death, many people starved to death, they were still collecting seeds for this project. And they could have eaten them, they could have done whatever, and yet they didn't. So you're among very, very esteemed intellects throughout history in that choice. Last question also harkens to Sir Arthur C. Clarke, and that's actually the name of the podcast. Yeah. The name of the podcast is Into the Impossible, which is Arthur C. Clarke's third law. His first law is any sufficiently advanced technology is indistinguishable from magic. The second one I already said. Yep. And the third one is the only way to find out what's possible is to venture beyond them a bit into the impossible. So my question to Adam is we went forward in time. Let's go back in time. What would you tell sort of a 20-year-old, 30-year-old Adam Riess? What wisdom would you say that seemed impossible to you at the time, but then you went ahead and did it?
Yeah. To be very honest, I knew I liked science. I found this subject very fascinating, but I didn't really think there'd be a place or a career, or, an actual way to do science, to be there very long. I just thought these are great courses to take. I love going to, my physics courses, and I love learning about these things, but, you can't. At some point I got to, grow up and get a job. And I guess I would say to myself, keep following your passion. I know it's cliche, but, in my case, it was literally true. Yeah. Don't give up until, the door's been slammed 100 times. And so, I guess it would be that.
That's great. Okay, Adam, I think that brings us to the end of our discussion. Are there any other things that I could have asked you, should have asked you, didn't ask you that you'd like to bring up?
Let's see. So what happened? So you won. So when we were at that contest, you won first prize, and I think you got some prize money or something. What'd you do with the prize money? Oh,
I spent it on my yacht, the SS Keating. No, what did I do with that? Well, actually, to be honest, I did. So I'm a practicing Jew. I'm not an Orthodox Jew, but we have a tradition, a mitzvah, if you will, to give away 10% of our winnings, and I did do that. I think it was like $20,000 actually, and this is in $2005 dollars, right? Not the funny money we use today. I think I gave some of it away, and I think I did buy. A pretty nice bike. I actually still have the bike that I bought. It was pretty fancy, and I can't remember. It was before kids, so I probably would all be gone now. On some iPads or whatever. Yeah. What'd you do with your share of the Nobel Prize?
Yes, that's a great question. I guess money's kind of fungible. You sort of what do I do with this piece of money? Believe it or not, I mean, it's a lot of money, but, it's still at the level you go, well, if both my kids go to college and, want to retire someday or whatnot, better kind of, keep that in the bank. So, I didn't do too many dramatic things with it.
Okay, great. Any other things you want to discuss before we sign off? Hopefully we'll get another chance to do this again soon.
No, stay safe.
Yeah, thanks, Adam. Adam, thank you so much, sincerely. You are, again, a role model, even for people that are basically your age, like me, that the work that you do has great meaning, and the fact that you do it with such consistency, regularity, you have great habits and these tactics and so forth that we talked about. You're really one of the menschiest mensches that I know, and I want to just thank you for sharing so much of your time with us today.
Thank you.
Thanks.
Take care.
Any sufficiently advanced technology is indistinguishable from magic.
If you enjoyed this episode of Into the Impossible, please subscribe, comment, share, rate, and review. For a chance to win a free copy of our most recent guest's newest book, send a screenshot of your review to info@imagine.ucsd.edu. We appreciate hearing from you and are always open to your suggestions for future episodes. For more information, go to imagination.ucsd.edu. Find us on Twitter @ImagineUCSD. Watch us on YouTube, listen on iTunes. Into the Impossible is a production of the Arthur C. Clarke Center for Human Imagination in the Division of Physical Sciences at the University of California, San Diego. Eric Veary, Director. Brian Keating, Co-Director. Patrick Coleman, Associate Director. Produced by Stuart Valco.